I welcome all of you to today's webinar on polymers about the DMA technique of viscoelastic materials. Before we start, I would shortly like to introduce myself. My name is Tobias Pflock. I work for Netsch Gerätebau in Selb in Germany, where I have a position as an application scientist. As you might guess, I work a lot on the DMA, and my mission that I want to tell you today is that the DMA technique can tell you more than you might eventually think. My education background is I have a physics degree from the University of Bayreuth in Germany. I also continued there for my PhD thesis in laser spectroscopy in Bayreuth and also at University of Glasgow in the UK in Scotland. And since 2011 I joined Netsch in the applications laboratory where I now work. What you see here is an overview of the workflow of the polymer industry, and this is just supposed to give an overview of the different parameters or properties that you would like to investigate and where all you could apply our devices that we offer for thermal analysis. And I would like to draw your attention on two things. So of course we talk about DMA today, so you can apply this already in the quality control, but most of the time dynamic mechanical analysis is applied in the final product to maintain a certain quality standard or application range and so on. This is what will be part of the talk today. Why is the DMA so important? This picture, I guess some of you know that, shows the explosion of the Challenger space shuttle in 1986, so quite a while ago already, but concerning material properties, I would say still up to date. As some of you know, the spaceship exploded as one of the fuel tanks was leaking out due to a leak in a sealing, and this in the end led to the explosion of the space shuttle. Why was that? Because they started at temperatures at this day, they had freezing ambient temperatures, so the rubber was not as it's supposed to be. And this is exactly where the DMA comes into play. For that, I would like to cite the report of the famous Rogers Commission that investigated the technical origin for this catastrophe in the end, and it states the O-ring resiliency is directly related to its temperature. A warm O-ring that has been compressed will return to its original shape much quicker than will a cold O-ring when compression is relieved. So this resiliency is exactly a mechanical material property. And from this investigation it followed that this material property is significantly depending on the temperature. So this is exactly where the DMA comes into play, because this is what you determine with the DMA. The temperature-dependent mechanics of a sample, in this case of an O-ring. So here I have a textbook definition of the DMA technique. Dynamic mechanical analysis provides information about the viscoelastic properties of a material under a small, mostly sinusoidal load as a function of temperature, time, and or frequency. So what I will talk about in the next half hour is what can I measure with the DMA. So this is a measuring instrument, so it will give you some numbers, so we have to know what these numbers have to do with the viscoelastic parameters of my sample. Secondly, of course, I would like to show you how I can measure it, and with that I would like to introduce the DMA that we provide, our Netsch DMA 242E Artemis. And as a third point, I have 3 application examples. The first one will be concerned with the glass transition of a polymer and how I find it. The second one will be concerned with the curing of a thermoset and how I can decide with a DMA when it's fully cured. And the third one will be concerned with the influence of fillers on the mechanical performance of a rubber. So what can I measure with the DMA? What are viscoelastic parameters? So we start with some basics. How can I understand viscoelasticity? On the one hand, elasticity, I can understand if I look at a model system that consists of a spring. This spring reacts if I just put some stress on it. It will just react with a deformation, and this deformation will stay all the time, and when I release the stress, it will just go back entirely and back to its original state, so fully reversible. This elasticity can be characterized by the ratio of stress over strain as a spring. A quite different property is what we call generally viscosity. I would call it for a solid more like plasticity. In this case, the model system that we look at is a dashpot unit you see here with a certain viscosity eta, and what happens here is quite different from the spring. I push it and it will just gradually deform, and in the end, if I release the stress, it will just stay like this. So this is a fully irreversible change that it does here. So now we know generally polymers are viscoelastic. So we can think of a viscoelastic polymer as a combination of elastic springs and viscous dashpots, as it will show both the behavior, a spring-like behavior, and also a dashpot behavior. We will see how that looks like if we do now a DMA experiment. So what we do is, as I said, mostly sinusoidal excitation. We apply a dynamic stress as a sine wave here. This is the dashed line you see here as I go along. And what the material will do, our viscoelastic polymer, it will react with some deformation. That is also a sine wave with the same frequency, but now it's a little bit retarded, and we can express that mathematically by that phase factor delta. So this is exactly how the viscoelasticity shows up in a DMA experiment. Viscoelasticity leads to a retarded sample response. And now, let's say all we have to do is we have to quantify that. We have to get some numbers that we can measure, and in order to judge the viscoelastic properties of our sample. What we want to do is we want to calculate the complex modulus. We have the stress, we have the strain. The modulus is defined as the ratio of stress over strain. I mentioned that. And in the end, as this is a complex number, I would skip that and just let the miracle occur. You can see that in any kind of mechanics textbook, of course. And I guess many of you know how that is solved. We can divide our complex modulus in 2 parts. The real, so-called real part, that we just call E prime, and the imaginary part is E double prime. These 2 numbers, if you look closer, are calculated as follows, and there is no big secret behind that, because this is all something that we can measure. We can measure the stress here, sigma, we can measure the strain eta, and we measure this, so we can measure E prime and E double prime, and this is exactly what the DMA does. One more. People often look at the tangent of the phase delta, so this is defined as E double prime over E prime. The secret about the DMA technique is now that with this mathematical trick, we have these different values. We now have to understand what this has to do with the viscoelasticity of our sample. So I would just make this, refer to this experiment here. So you take a, let's say, a rubber ball, and you just drop it on the floor. What will happen? It will come back up. And this is how the parameters are linked with the property of a material. The way the rubber ball comes back up is exactly proportional to the amount of stored energy and the spring-like response of our material, of this rubber material. And this refers exactly to the storage modulus E prime. This is why we call it storage modulus, because it refers to the stored energy. The part that is left is proportional to the dissipated energy, and this refers to the dashpot-like response. So all parts of a polymer that act like a dashpot will dissipate this energy. So this number, E double prime, is therefore called the loss modulus E double prime. As this is, I think, so important, I would just sum up the viscoelastic parameters again. The storage modulus E prime tells us exactly about the elasticity or the stiffness of a material, and is proportional to the energy that is stored in the material during one period under load. The second parameter that we look at is the loss modulus E double prime. That refers to the plasticity for solid or viscosity of a material, and it's a measure for the ability of a material to follow a deformation without breaking. It's proportional to the work that is dissipated during one period under load. And the third parameter that we look at, that you see in basically all DMA graphs, is the loss factor tan delta, and this characterizes the damping or internal friction of a viscoelastic system. So on the next slide, I will show you what a typical DMA measurement looks like. What we do here is normally we do a temperature sweep, so we look at exactly the properties I just mentioned as a function of temperature. So the temperature axis is the x-axis here, and the storage modulus in green, E prime, is just this green line here. You see it's very high here, and then it drops over more than 1 order of magnitude. You can see in blue the loss modulus that just has this peak, shows this big peak here, and followed by that is the peak of the loss factor tan delta. So it's quite clear already that with the DMA I can investigate the mechanics of my sample as a function of temperature. So I guess many of you already know what we see here. This is nothing else but the glass transition of an elastomer sample. So this is how the glass transition shows up in a DMA measurement. The glass transition is the change from a glassy state of the material where it's very elastic or very stiff, and where all movements of the polymer chains are frozen, along this huge drop where it greatly softens along the glass transition in all three parameters, and we end up as for this elastomer in the rubber elastic state, where the polymer chains are free to move and they maintain the actual elastomer properties that we want. Okay, how can I measure these properties now? How does the DMA work? This is what our DMA looks like. This is a DMA-242E Artemis. And in order to understand it, we will take a closer look. This is what it looks from the inside. So what do we need? We need an oscillator to generate some force. And this force will be transduced via this push rod onto the sample. And in the sample holder where we have our sample, the sample will act with some displacement that we can measure with the displacement sensor. And from the force and from the displacement, we can calculate our modulus. As I said, we do thermal analysis, so we want to investigate this as a function of temperature. So down here, you can see the furnace of our DMA that is it's pulled out now, so you can just goes over the sample holder here if it's an operating mode. If not, you can just push it in parking position and very easily remove your sample or change sample holders and so on. And I would like to draw your attention to one more point, and that is the stepper motor that we have built in, that is just moving this whole dynamic part up and down. Why is that so important? Imagine if your sample softens during the investigation, so along the glass transition, in order to test the mechanical properties, you would still have to be in contact with the sample. So this stepper motor just moves the whole unit as the sample softens and will maintain the contact. So you will actually never lose contact with your sample during the measurement. On this slide, you will have an overview over the deformation modes that you can have. Just shortly mention them. Compression or penetration mode, 3-point bending, tension mode, shearing mode, and a single and dual cantilever mode, where the sample is clamped on either one side or on both sides. So with that, you can already see that this is quite flexible concerning your different sample shapes that you have. I would just take out a few sample holders and look at them in more detail for what they're used for. This is 3-point bending, where you have free supports here. So in this case, you will not be influenced by clamping effects during your measurement. It's very suitable for measuring stiff and hard samples that don't get too soft above the glass transition. For example, fiber reinforced and highly filled thermoplasts and composites from that, and also thermosets. And from that, I will have an example in my application examples later. The second one is tension, that I use quite commonly. I use that for fiber samples, for film samples, for packaging and so on, and also for elastomers. Well, I'll have an example later on in my application examples, or unfilled thermoplasts. That's what you could use the tension mode for. The last one, I think the most straightforward one, is compression with all different, so you just compress your sample with a fixed support, and there's different shapes. You can just get much smaller and even have this 1 millimeter shape here. You can use it for foams, elastomers, for softer samples above the glass transition temperature, and for samples with undefined geometry. So imagine you have failure analysis case, and you just have a very, very small part of your sample. You just have very few amount to test. So of course you need a very small push rod, so I would go with this 1 millimeter push rod here, for example, and determine the mechanics as a function of temperature. So we know what we can measure. The viscoelastic parameters, we know how we can measure it, so now I would go into some real-world examples. Where's the glass transition? So this will be my first application example. I will be talking about a thermoplastic elastomer. So what is that? Thermoplastic elastomer, in this case we talk about a thermoplastic polyurethane, is a rubber that can be melted, in short words. So the idea is that the crosslinks that form the rubber are actually thermoplast crystallites that you can just melt, and by that the idea is of course that you have an elastomer that you can process like a thermoplast through injection molding and extrusion and so on. So what is the question here? The question is about the glass transition. Why do I look at the glass transition temperature? Because the glass transition limits the application range of my elastomer, because we know that below glass transition temperature my elastomer will lose its rubber properties, so it will just be frozen. So this glass transition will limit my application range. So I said, well, here I did a DSC measurement on the sample. So this is the thermoplastic polyurethane sample. And the question is now, where is my glass transition? So this just increases here. There's a small bump at about 50 degrees. And at about 150 degrees, you might have already guessed, what you see is an endothermal peak. So this is the melting peak of exactly my thermoplast crystallites as the thermoplastic elastomer melts. However, the question remains in the DSC, where is the glass transition of my polymer? So the picture is somewhat different if I look at it in a DMA. So it's exactly the same sample. What you see here now is the DMA measurement. You can see in the green curve with the same color the storage modulus of the sample. In blue you can see the loss modulus, and in red the tan delta curve, the loss factor as a function of temperature from minus 150 to about 220, 210 degree. So question again, where's my glass transition? We noticed before that the glass transition shows a significant drop in the storage modulus. So I just lose the elasticity of my sample. It just gets soft. So right in the middle, this is of course where my glass transition takes place. You can already see that, well, this sample is already quite a complex material. TPU is not an easy polymer, definitely not. But from a DMA, you can easily see the glass transition because the mechanical behavior is most sensitive to the glass transition. So I would even say, if you do not see a glass transition in the DMA, there is no glass transition. So we could take a closer look and evaluate the sample a little bit different, which I did here. It's just the same graph as you saw before. However, the storage modulus in green is plotted logarithmically. This is also what you see quite commonly in order to better investigate the region here at lower temperatures where the signal is lower. And what you can identify from this curve is, as I said, the glass transition at about minus 15 degrees Celsius, but we can see more in the mechanics. we can see a beta transition at minus 110 degree, and beta transition refers to a movement of polymer side chains. So you can actually have a tool to look into the chemistry of your polymer. And in the end, again, where it greatly softens, you see the crystallite melting of your sample at about 139 degrees. So afterwards, the sample is really soft. And this is all just from the DMA. So let's compare this now to the DSC measurement. This is what you can see here. It's just the same DSC curve. I just plotted it on top of each other. In petrol is the DSC curve, and in green, blue, and red is the DMA curve. And now we can identify the glass transition also on the DSC. And you can, with some, let's say, goodwill, also see a glass transition at lower temperatures at minus 83 in the DSC to correlate that to your beta transition. And of course, you see the melting peak. But what I want to point out is why I showed this example. The DMA can directly show you the mechanical application range. So I hope it is obvious to you that DSC is a very powerful technique, but it's an indirect technique. And with the DMA, I can just see when my TPU sample is just frozen and I cannot use it anymore. So where's my application range? It's, of course, exactly in between my melting of the sample at about 120, 139 degree, down to, let's say, about 10, 20 degree, where it just gets too cold and the sample gets too stiff. So the DMA directly shows you the mechanical application range. In my second example, I would talk about the curing of a thermoset sample. What is a thermoset? A thermoset is an insoluble polymer network with a high density of chemical crosslinks. So now I want the polymer to be frozen, to be cross-linked, highly cross-linked, so it's a very stable polymer. Where is it used? Thermoset resins are often used as polymer matrix, and for example adhesives and so on, in this case for fiber reinforced composites, so carbon fiber reinforced polymers, glass fiber, any different fiber. There's a few examples here from these windmills where you know that mainly glass fibers are used, but in the automotive and to the top right and in the aviation to the top left, you know that also carbon fiber reinforced polymers play quite a big role. Why do we do it? Because we have a high structural stability at low weight and low density, and the aim is, of course, at lower cost. So what can we do with the DMA? We know already we can determine mechanical parameters. We can measure the stiffness at a certain temperature. We can measure the loss modulus and the damping. We can also measure the glass transition to determine the application range. And we can look at curing behavior. How do we see that? This is just a measurement on a thermoset. You see the storage modulus as this black line here. You can see the loss modulus as the dashed line, and you can see the loss factor as the dotted line. And you see again in the storage modulus a significant drop over here, in this case more than 2 orders of magnitude. So, well, the sample gets soft. So what is that? That's the glass transition of my thermoset. So I would not obviously, so this is what determines the application range, because I would not necessarily build an aeroplane at that has to stand temperatures of higher temperatures with that kind of thermoset that you can easily tell from this graph. So we know the glass transition, but I said there's more, because now we can do thermal analysis. So we just take the same sample and we just heat it once more. That you see in this graph, the black curve is the first heating, the red curve refers to the second heating of the sample. And if we look at the application temperature, let's say at room temperature, at 25 degrees, we see a significant increase in the storage modulus due to the second heating. So what is that? That is, as the topic already says, this is nothing else but post-curing of the resin matrix. So my polymer is not fully cured. I heat over the glass transition. There is more chemistry going on due to diffusion. I cool it. I heat it the second time, and in the second it's changed irreversibly due to the build-up of more crosslinks. So this leads to a higher stiffness, and this is exactly what I see in my storage modulus in the DMA. So is it fully cured? I can just check with the third heating, and the second and third are just on top. So the red and the blue curve are on top of each other. So I can see, yes, the part is fully cured. There is no significant change anymore. So with these circumstances, I know that my part is fully cured. The last example is about how fillers influence the performance, in this case a rubber sample. Why would you use fillers for a rubber? Well, generally you can say this improves the mechanical properties, and this is exactly, as I stated, what you can investigate with the DMA. In this case, we look at a system from styrene butadiene rubber together with some nano things. So in this case, we use multi-walled carbon nanotubes as a filler. Why nano? Because we think in this case, well, you hear nano around quite often these days, but in this case, we expect it to have a better interaction on the microscopic level with the polymer matrix. So we expect a large influence of nanofillers on the mechanical properties. I would just like to acknowledge this to Professor Bokopsa, with who we did this project and who provided the samples for us. Thank you for that. This is what the samples look like. On the left, you see the pure SBR rubber. On the right, you can see, due to the black color, SBR plus carbon nanotubes. And if we take a closer look, we can actually see what's inside. So this is a very close look on the microscopic level already, where you see a picture of a transmission electron microscope, and you can actually see these multi-walled nanotube network inside the polymer rubber. So we expect, again, this makes a dramatic change to the mechanics. And well, we just look at it on the DMA. This is what we did. The experiment that we did is for the different curves that you see, we gradually increased the content of carbon nanotubes from the black curve, which is pure rubber, to about 15 PCE, which is parts per 100 rubber. So it's 15 weight% of rubber. And you see, obviously, there's an influence. What we see here in the middle, again, to characterize the material, is the glass transition. Glass transition temperature is the same because we do not change both materials, but we see a strong increase below the glass transition temperature of a factor of 3. The important thing is, again, the scaling here is logarithmically. So what you see, this increase here at room temperature is quite strong. This is a 3,000% increase of the storage modulus of our material at room temperature, and I would call that significant. And this is what you can easily investigate with the DMA. The second graph we look at is the loss factor, so you can also investigate damping of your material. You can clearly see that the damping peak at the glass transition decreases for higher carbon nanotube content, but again, at room temperature, you can definitely, at the application temperature, I would say you can definitely see a better damping material. So I would say it's a better material. And I think this is a nice comprehensive study of the effect of fillers with the DMA. So this is the end of the DMA part of what we just learned. So I would sum up. We can measure, let's put it different. The DMA is the only device where I can take apart the elastic response with the storage modulus E prime and the viscous response with the loss modulus E double prime, and again measure the damping in order to characterize the mechanics of my sample. It directly displays the mechanical properties, for example, as a function of temperature. So it's not an indirect method, but I can directly determine my application range. And I try to show you that the DMA is most sensitive to any mechanical influence on the microscopic structure, such as, for example, filler interactions, cross-linking state, crystallinity, the effect of humidity uptake, for example, plasticizers, polymer blends, and so on. There's, of course, many more applications, but this is all something that you can see in the DMA. There's some more things that I did not have the time, of course, to talk about, and that would be that the DMA can not only tell you about, well, E prime, E double prime, and 10 delta as a function of temperature, but also as a function of frequency, for example, because the frequency is makes a significant effect of the mechanics of my sample. Even more, with our DMA, you can not only look at dynamic deformation, but also at static behavior, such as basic experiments like relaxation experiments and like creep experiments, for example. And you can do more. You can do multi-frequency measurements and derive some values about time temperature superposition and construct master curves and so on, for which I did not have time now to get into it. So our answer to that is the DMA that I show you here once more. We say it's the most versatile DMA in the world. It's the DMA-242E Artemis from NETCH. And I would just sum up the key features. We have a controlled force range up to 24 Newton. And interestingly, this force range is significant to determine the modulus values for a wide variety of materials over, I think 6 orders of magnitude. So this is a very powerful technique, from, let's say, stiff metals, very highly filled carbon fiber reinforced polymers, down to something like a soft rubber sample or some pasty sample, for example. So this is all possible with one device. We also, I mentioned that at the beginning, have a static travel range of 20 millimeter with our stepper motor, so we can do in the range of the force we can apply also static experiments. We have more than 30 different sample holders available for our DMA, so this can be applied for any kind of sample geometries. We have a wide range of accessories. There's a humidity generator that can be ordered with it in order to control the humidity, which is a crucial thing if you have a strong water uptake of your sample. You can have a UV lamp with it to look at UV curing or UV post-curing. and DMA-DEA coupling. DEA refers to dielectric analysis. That shows you, so you can look at both mechanical and dielectrical curing in one and the same experiment. With this, I would still refer to the DEA webinar again. That will come up in about a month, so please sign up for that. And we have an immersion bath that allows to immerse your sample in different kinds of media. We have chosen a hang-down design, so all the mechanics is in the upper part, and the sample is easily accessible if you sit in front of it from the bottom. You just put this furnace into the parking position, and you can very easily remove the sample holder and assess your sample and change the samples and so on. We can measure under defined atmosphere, so you can nicely purge this. And I think we have a comprehensive software package with it where we can get out the significant parts in the analysis. So you already saw that you get 3 parameters at once. So you have several kinds of measurements. So it's not too easy to take these measurements apart with our analysis software. I think this is programmers did a good job, and you can very fast take this apart and interpret your sample. So with that, I would like to get to the summary slide on dynamic mechanical analysis. What I tried to show you today. There's different applications of the DMA in material development, quality control, failure analysis, and coming up more and more, determination of material properties for mechanical simulations. The instruments that you need, I just showed you, is DMA and some accessories as humidity generator and so on. The materials you can investigate go through the entire range of polymers. Of course, what I did not mention, also biopolymers. Food is also biopolymer in some relations. Thermoplastics, of course, polymer blends, thermosets, I showed you an example, coatings, elastomers, thermoplastic elastomers, one of my samples, composites, fiber reinforced composites, which are quite up to date right now, but also other materials such as the response of metals or ceramics and their composites. In the end, you get information on storage and loss modulus values. I hope I could show you what that is. On the mechanical damping, the glass transition to investigate your application range, recrystallization and crystallinity as they show up in the mechanics, vulcanization and, well, cross-linking of rubbers. That shows up in a DMA measurement. Thermal stability, you can also degrade your sample and see when it degrades mechanically. There's more, which I could not talk about today. This is multi-frequency data as a function of the frequency, where you can derive master curves. You can look at static modes such as creep and relaxation. And in the end, you can also turn off your oscillation mode and look at thermal expansion in some respect. So we're about at the end of our webinar. Still, this is the link that takes you to the landing page on our homepage about the DMA, where you can also get more information on the DMA technique. There's more application examples that you can download, or you can also get easily in contact with us if you're interested in the DMA technique or other techniques of thermal analysis. And with that, I would like to thank you for your attention.